Yesterday you guys did this lab, and I think you did a pretty good job on the front page. I talked to Jay, and static friction is the force you have to overcome to start an object moving, and kinetic friction is the force that you overcome to keep an object in motion. But friction always opposes motion or intended motion. So if the thing's not in motion and nothing's trying to make it move, there is no friction, which is what number one's getting at. If it's at rest and if there's no forces acting on it, then there's no friction because there's no need for friction. There's nothing trying to cause it to move. 2 says, hey, if it's a 0.49 Newton force to start to pull it and it still doesn't move, that means friction must be pulling back against it with 0.49 Newtons. And 3, if you've got this thing moving, or it just starts to move when you apply 0.98 newtons, then it must have taken 0.98 newtons to overcome friction, so the maximum static frictional force is basically 0.98 newtons. 4 and 5, that's just things that you guys probably already know. Okay, and then you set it up, you did some stuff, and you got some data. Now I do want to take a look and point out some stuff here. This right here, okay, that spot down at the bottom, that's where the thing hasn't started to move yet, so that's no force. This is where you're increasing the force, but the block doesn't start to slide. But right here where we get this spike, it starts to move, and then right here it's moving at a constant speed. And I think you guys did that okay too. Alright, then you had some data to collect. Man, that was interesting. Freaked out. Okay, then you had some data to collect, and so you guys just used the force probe to pull the block along the table, and you got data, and Jay actually emailed me the data. I asked him to do that, and so the next part of this lab is to take all your data and figure out what was actually happening. And so there's some questions here. Using your force versus time graph, was it harder to start the block in motion or keep the block in motion? Okay, well, you needed a bigger force to start it and then less force to keep it moving, and that's probably what you thought. Okay, it's harder to start something in motion than keep something in motion. The coefficient of friction is a constant that relates the normal force between two objects and the force of friction. Based on your graph from part 1, would you expect the coefficient of static friction or the coefficient of kinetic friction to be bigger? And since it took more force to start it moving, we would expect the coefficient of static friction to be bigger. Okay. Now part 3 says calculate the normal force of the table on the block with each combination of added masses. Since it's a horizontal surface, that's just normal force is equal to the weight force, which is mg, and so you guys took mass times the acceleration due to gravity, did that, and your data looked good on that. Now 4 and 5 say, okay, let's plot a maximum static friction force versus the normal force. Use the LabQuest graphical analysis or graph paper. Okay, since I have your guys' data, what I was able to do is just go into graphical analysis, and so if I do that, I'm going to show you how you could do this. Okay, graphical analysis is right here. And there's your data. I'm actually looking at it right there. But to do that, all I did was I said, okay, I want a new manual entry. Okay? And in the X column, I wanted to rename that. So the X column I called normal force, or just normal. And then the units I wanted were newtons. And then Y I had static friction. Okay? And again, newtons, and then I just push the little plus button and I can get another column in here, and this was kinetic or sliding friction, and again this is a force, so measured in newtons. Alright, and then I just put in your guys' data, so 1.18, 6.08, 10.98, that was the normal force, 0.323, 1.547 and 2.62, and then finally kinetic 0.257, 1.138 and 1.96. Okay, and done and done. And so then I wanted to see the graphs, so up here at the top I push the graph button and I say, okay, show me a graph of that. And then I have to tell it what I want to look at. So on the left side it's already got static, and I want to see that versus normal. Okay, so now it's got static versus normal, and you can see it plotted those 3 points. And if we take a look and highlight those 3 points, they look fairly linear, so I'm just going to do a curve fit, and I'm going to say linear. Okay, and so now I've got this line, and yeah, those points are pretty much in a straight line. And over here, it tells me the slope of that line. Okay, that's relating the static frictional force to the normal force. So by definition, that's the coefficient of friction. So of static friction. Back on my lab, okay, it says, okay, plot a graph of maximum static friction. Did that since the maximum static frictional force is equal to the coefficient of static friction. The slope of this graph is the static friction coefficient. Find the numeric value of the slope, including units. And so, I can't remember, that was 0.234. Now, what are the units of that? Okay. Well, think about it. Okay. We took rise over run, and the rise was static frictional force divided by the run, which is the normal force, and those units cancel. So my coefficient of static friction, my mu s, is 0.234. There are no units. It says, should a line fitted to these data points pass through the origin? Well, it definitely should. If there's no normal force, then the object is not sitting on a surface, and if it's not sitting on a surface, there's no friction. Okay. In a similar manner, do the same thing for the kinetic frictional force. So back in graphical analysis, now I actually want to look at static friction, and also I want to see kinetic friction. Okay, and if I turn that off and on a couple times, it changes the color for me. So now the red line here is static friction, and the blue line is kinetic friction. You can see they're both basically headed towards the origin on the left side, but the blue line isn't as steep. It's only got a slope of 0.174. Okay, and so down here, mu k is 0.174, and that's less than the coefficient of static friction. Okay, and it does pass through the origin, but why is it less? Well, kinetic friction is less than static friction. It's easier to keep something moving than start something moving. Finally, number 7, does the force of kinetic friction depend on the weight of the block? Yes. Okay, that's what the graph shows. Okay. If we go back, the normal force is really just the weight of the block, right? The more weight the block has, the greater the normal force is. As the weight increases, the line also gets up, and so kinetic friction and static friction get higher. The last question on the lab said, hey, does the coefficient of friction depend on the weight of the block? The coefficient does not. Okay, the coefficient's the slope of the line, and the line didn't change slope. It was a linear graph. It didn't get steeper or less steep. So no, coefficient is constant, but the force increases directly with the force, the normal force. Okay, there's actually a couple problems I wanted you guys to look at in your book. Mostly what I want to see is numbers 27 through 32 on page 130. Okay, so your assignment 27 through 32, page 130. Okay, and I'm going to work an example problem for you real quick. It's one of the practice problems on the same page. It's number 24. Okay, but this is just using Newton's laws, friction, and the tools of motion in order to solve some problems. So number 24 says a shuffleboard disc is accelerated to a speed of 5.8 meters per second. And so I have V naught equals 5.8. And then it says it's released. The coefficient of kinetic friction between the disc and the concrete cord is 0.31. So coefficient of kinetic friction equals 0.31. How far does the disc go before it comes to a stop? So it comes to a stop. Final velocity is 0. We want to know a delta x. Question mark. Okay. Now if I look at that, I can say final velocity squared equals initial velocity squared plus twice the acceleration times the change in position, but I don't have the acceleration, so I need the acceleration. I know that there's a kinetic frictional force acting on this disc, right? So the shuffleboard disc is moving this way. There's weight pulling down, okay, and then there's the normal force pushing up, and then there's friction trying to slow it down and stop it, so Fk. And so I'm supposed to figure out what the acceleration of the block is so that I can get this change in position. Okay, so to do that, I'm going to say, well, the normal force is equal to the weight force. So I basically have Fn equals mg. Okay, and I also know that kinetic friction is equal to the normal force times the coefficient of kinetic friction. And so I can say Fk equals mg times mu k. Okay, but I don't know Fk, I don't know m, and so this looks like two unknowns. But Newton's second law says net force equals mass times acceleration, and since this force and this force cancel, the net force is Fk, so I can say this equals ma, and so from there I can say, okay, mass is on both sides, I can cancel that, and I get g times the coefficient of kinetic friction equals the acceleration of the block. So I've got 9.8 times 0.31 equals a, and if I just do that calculation real quick, 9.8 times 3.1, I can get the accelerate, whoops, not 3.1, 0.31, okay, so 9.8 times 0.31, I get the acceleration of the block is 3.038, and so now a equals 3.038, but I have to be careful. Okay, nothing about this math showed me that this was negative, but I'm looking at my picture and I know it has to be negative because it's against the initial velocity. So now I can use my equation, final velocity squared equals initial velocity squared plus twice the acceleration times the change in position. So 0 equals 5.8 squared plus 2 times negative 3.038 times delta x. So 5.8 squared is what? Right around 34-ish. So this is about 34 minus 6.076 delta x. So 34, negative 34 divided by negative 6 is about 5.8, and I'm just estimating here. So that's interesting, but 5.8 meters. So the shuffleboard disc goes 5.5, 6 meters down the court. I think I did okay on my estimations. Okay, but you see how this works. To me, the trickiest part to this whole problem is when you had to figure out that the masses would cancel since the masses weren't given to you. Okay, but good luck. I want you to try those 27 through 32 on page 130. If you have any trouble, let me know.